Okay, let's talk about the electromagnetic spectrum, which is just referring to a whole range of different radiation. And radiation exists in the form of waves. So there is a long list of different types of radiations here, which is given in your data booklet. And what I would suggest is that you only memorize these three: ultraviolet, visible, and infrared. And of course, it's useful to memorize all the colors of the rainbow with Roy G. Biff. Now, if you've taken physics, you can probably skip the next minute or two of this explanation. If not, I'll give you a quick rundown about wavelength, frequency, and energy. The definition of wavelength is the distance between two identical points or crests in a wave. For example, this line here is a wavelength. This is a wavelength, and this is also the wavelength. So in this diagram, from left to right, the wavelength is going from shorter to longer. Now let's monitor the relationship between wavelength and frequency. Frequency refers to the number of times that an event occurs within a period of time. So what we're going to look at here is how often this wave goes up and down within a period of time, which I've denoted as the red box. So going to the box on the right, we see that we have a long wavelength, and the frequency is also really low. This wave only goes up and down about once or maybe 1.5 times. And then in the box in the middle, the wavelength is intermediate, and going down to the left, the wavelength has started to become shorter. Look at the frequency. The wave has gone up and down multiple times, around 6 or 7 times. And at the box on the far left, the wavelength is the shortest. And you can see that the frequency has gotten really high. It goes up and down numerous times. So this is the first relationship. There is an inverse relationship between wavelength and frequency. And that's denoted by this formula, C equals lambda V, where C is the speed of light, which is given in your data booklet. Lambda is the wavelength, and V is the frequency, right? So the speed of light is constant. So you can think of the relationship between frequency and wavelength as being frequency equals to C over lambda. The next relationship we want to look at is between frequency and energy. So the analogy I like to use is a basketball. Let's say you're bouncing a basketball pretty gently, so you're not putting a lot of energy into the ball. You find that the ball bounces pretty slowly and gently. So that's analogous to the box on the right here. So you don't put a lot of energy into it, and it bounces slowly. It touches the ground with a lower frequency. Now, as you put in more energy, so you're bouncing the ball on the floor harder and harder, the ball starts to bounce faster. The frequency that the ball touches the floor increases. And that's the relationship between frequency and energy. The more energy you give a wave, the higher the frequency. And the less energy you give a wave, the lower its frequency. It's denoted by this formula, E equals to hV. E equals to energy, H is Planck's constant, given in your data booklet, and V is the frequency. C equals to lambda V and E equals to hV are both in your data booklet. Now, if you notice, V appears in both formulas, so you can actually combine them to give you another formula, E equals to H times C over lambda. So, long story short, the longer the wavelength, the lower the frequency and energy. Frequency and energy are inverse to wavelength. So vice versa, the shorter the wavelength, the higher the frequency and energy. And how do we apply this into a question? Let's take a look at this question. Let me write down the formulas here. Now, one thing you have to note is to convert everything into SI units. So wavelength, lambda, is given in meters, frequency in 1/second, and energy in joules. The speed of light is in meters per second, and Planck's constant is in joules second. So let's look at this question. We have radiation with a wavelength of 500 nanometers. And the first thing we do is convert 500 nanometers into meters. And to do that, we have to multiply it by 10 to the power of negative 9. And we end up with 5 times 10 to the power of negative 7 meters. Next, let's plug this into the formula E equals hc over lambda. So energy will be Planck's constant, which is 6.63 times 10 to the power of negative 34, times the speed of light, which is 3 times 10 to the power of 8, and lastly divided by our wavelength, which is 5 times 10 to the power of minus 7. And the value that you should get is 3.978 times 10 to the power of 19 joules. It's simply a matter of ensuring that the values you have are in the SI units, and then subbing in values into the formula. Now let's try another question, and I'll provide you with the formulas here in case you need them. Pause this video, take a couple of moments to figure out the answer, and I'll be back to go through it with you. All right, so let's take a look at this question. In the previous question, we had wavelength, and this time we have energy. And just checking that the SI units are correct, it is in joules, so no problems with the units here. Our job is to find wavelength, which is lambda. So the formula that connects energy with lambda is the third equation here. But let's rearrange this equation such that lambda is the subject. And we end up with lambda equals to Planck's constant times the speed of light divided by energy. Planck's constant is 6.63 times 10 to the power of negative 34. The speed of light is 3 times 10 to the power of 8. And the energy given to us is 9.945 times 10 to the power of 19. And when you plug these values into the calculator, you get a pretty nice, simple number of 2 times 10 to the power of negative 7 meters. To convert this into nanometers, if you prefer, you just have to multiply it by 10 to the power of 9, which is equals to 200 nanometers. Wavelength can be given in meters or nanometers. Just watch out for what the question says because sometimes they do specify the units. But both 2 times 10 to the power of negative 7 and 200 nanometers will be accepted. And that is it for the electromagnetic spectrum.